Let's talk about how can we store an analog signal using bits in a computer. Let's start, for example, with sounds. A sound is a wave, and a wave is a signal that varies over time. So, for example, we have time here. This is the value of the signal, and this could be a sound wave. Okay, it can have different frequencies, different amplitudes, whatever. The problem with a continuous signal is that between any 2 points, for example, between here and here we have an infinite number of points. And of course, we can't use an infinite amount of bits just to represent a teeny part of the signal. But of course, computers can record and reproduce sound. So how it is done? I'm going to show you an example. I'm going to record a sound. This is a sound. And I will change the visualization. And you can see here that the computer has been able to generate a waveform. This wave is the sound I was generating with saying the phrase. But if we zoom in a little bit more, here we can see that the wave is not continuous. It's made of points. Here you have some points, and uh, with these points we can more or less reproduce the form of the signal. Okay, but between any 2 points, we don't know what were the value of the signals, but we assume that it is continuous and we can reproduce the signal. This technique is called sampling because what we are doing is taking samples of the data at a determined interval. So for example, we have the signal. We can choose this interval for taking samples, and here, more or less. And we will store the value of the signal at these points. Okay, so when we need to reproduce the signal, what we do is to draw the points and extrapolate the values between them. So what's the important thing about the sampling interval is that the greater the sampling interval, the less fidelity we will have for reproducing the wave. So if we pick, for example, a greater sampling interval, for example, we pick this interval, okay, we will store only 3 points, but it will be difficult for us to reproduce the value of the signal. We don't know if it's that this way or is this way, or you can have a lot of signals that a lot of signals that passes that pass through those points. But if we increase the frequency, if we have a smaller sampling interval, for example this one, we will have a lot of points. It will be easier for us to reproduce the signal. In this case, we will have almost. It will be easier to draw here the form of the wave, but we will need much more information to store. For in this case, it will be 1, 2, 3, 4, maybe 5 times the values that we will need if we pick a longer sampling interval. How much data we will need to record a sound? Well, the frequencies the human ear can hear varies from 20 to 20k hertz. So there is a theorem, the Nicky's theorem, told us that to being able to reproduce a signal, we need to sample it at twice the signal rate. So in this case, we will need at least 40k sampling the signal at 40k hertz. We usually sample the sounds at 44 0.1 kilohertz. Okay, this is the usual sampling signal, because with this we cover all the ranges, all the range of frequencies that we can hear. So we will need to take all those samples per second. Each sample the, will, in each sample we need to capture the value of the sound signal at that point. Uh, this we will need at least, it depends on the base noise and some other parameters, but at least we will need 16 bits to store a sound signal. This is a usually we need 24, we use 24 or 32 bits to store a sample, a single sample. So for 1 second of sound, we will need to spend 88.2 kilobytes just for 1 second. If we multiply that by 60 and we multiply that by 2, because this will be a single channel and we want to record a stereo signal, we need to multiply by that, and that give us around 10 megabytes just to store a single minute of, of sound. That's too much. So there are some techniques to be able to reduce the amount of the size we will need to store a recorded sound.